Okay, so a very good evening, everyone. So today we are into the seventh lecture and we are going to discuss communities in today's lecture. So let's start with our lecture today. Okay, so up till now, we have covered the basic centrality measures, the basic measures in which you can measure the properties of the nodes. Okay, so we have, tried to answer one of the very important question that was how would you identify the importance or influence of a node in the network? So for that, we have seen various algorithms like the degree centrality, closeness centrality, betweenness centrality, eigencentrality, and so on. And apart from this, we have also seen certain network measures like the density of the network, diameter in the network. Then we have seen the clustering coefficient. And also we have studied various different aspects that were related to social network analysis like small word network property. Then we have the distribution of degree, the power law distribution of degree. And so these were the topics that we have covered till now. Okay, so now in today's lecture, we are moving to a very important a very important property in the network, that is communities. So one question is, how do you identify the groups or the clusters in the community? So there is very important phenomena in the social networks that is called as homophily. So what is homophily? I will give you some examples of homophily. So for example, whenever you want to watch a movie, okay, so you have this weekend and you are searching for some web series or for some movie to watch on Netflix. So generally you ask your friends that what movies they are watched and what movies they recommend. So based on that, you choose the movie or the series you want to see. Okay, so that is the first example. So next example is, for example, you are moving into a new society. Okay, so suppose I am moving into a new society. I'm searching for a flat, and while searching for a flat, I got this flat, which I'm almost finalizing. And then I discovered that, okay, I have a neighbor who is Punjabi, and I'm also Punjabi. So I will be like little bit more happy to see that, okay, I have a neighborhood that has similar properties to what I am. Okay, so then like this is another example that I have myself witnessed a lot when I visit the international conferences. So whenever we visit the international conference, there will be people from different nationalities, right? So generally after the third or fourth day of the conference, we see that people who are maybe Asian, they group together. People who are belong to US, they form a group. So we see this kind of groupism in the conferences. Okay, so you can see that like in the social networks, similar people, they tend to connect with each other. Okay, similar people, they tend to collaborate and they tend to form a group with each other. Then there's next example from our real world life, that for example, you might be having some parks around your society or around your house where you live. Okay, so you might have seen that children, they will generally connect with children. Okay, so you will be seeing that if there's a child who is new to this park, when he enters the park, he will quickly form friends with other children. Okay, then we will see that there will be certain elderly people, they sit together and they form a group. Then we see certain middle-aged ladies, those who are walking together. So we see that these people, they form groups based on the age group. Okay, so we can say that in social network, there is a phenomena called as homophily, because of which the people with similar property, they tend to group together. Okay, so the tendency of individuals to associate and bond with similar others is called as homophily. Okay, so the homophily can be formed based on age, as I have told you in the example of the park. Then we have sex and genders, we have education, occupation and social, religion, race and ethnicity, interest, and organizations' roles. Okay, so for example, maybe in a university, you might have seen that professors they form a group and students they form another group. Okay, so there will be generally a group that is formed on similar properties. Okay, so this is the cause of formation of groups or the communities in the networks. Okay, so we see that the connections in the social networks, they are not random. So there is some kind of properties that are playing into role because of which we form certain groups in the network. Okay, so in today's lecture, we are going to further see that how are we going to identify these groups. I'm also going to motivate you more towards this problem of identification of communities in the group. So now let us discuss what are communities. I can define that communities are a set of people that are more connected within than the rest of the network. But actually speaking, the term community is very ill-defined problem. Okay, so why this is a ill-defined problem? Why I'm saying that this is a ill-defined problem? So you might have seen that like we have studied the definition of density. Okay, so what was the definition of the density? The definition of density is number of actual edges. Maybe if we are trying to identify the density of a group, so the density of the group will be the actual edges that are there in this group divided by total number of possible edges. Okay, so this is the definition of density. So now intuitively, you can think that communities have dense connections within as compared to other groups or other communities. Okay, so the like intuitive definition of communities is that communities within a community there will be more connections amongst each other than the connection with outside world or outside groups. Okay, so now, maybe we can, try to quantify the communities based on the density of the edges that are there within a single group. Okay, but at what point you will say that this is more dense, and at what point you will say that this is less dense? So you do not have that threshold defined. Okay, so you do not have a certain point which we can say that beyond which these communities are dense. So that is why identifying a very concrete definition of communities is difficult. So this is a very ill-defined problem. The only thing that we know is we want to form something, some kind of groups, and how these groups are formed that we are unaware of at this point of time. Okay, so now if this is a identification of community is a ill-defined problem, then this is both advantages and disadvantages for us. Why it is advantages? It is advantages because it opens a lot of doors for research. Okay, so you can actually research and you can actually come up with different algorithms for community identification in the networks. Okay, and the disadvantage is that okay, you have this algorithm that is convincing to identify the communities in the network, but then how will you validate that this particular algorithm is correct? So that is the disadvantage of not having a concrete definition to the communities. Okay, so now next, let us discuss the applications of community detection. We are studying the applications of community detection because I want to motivate you that this is a very important problem, and this problem will be used in in order to solve other problems in the social networks. Okay, so for example, we see that community detection plays a very important role in link prediction. Okay, so how it plays an important role in the link prediction. For example, let us suppose I have these three groups. Okay, so let us suppose I have this network and I have these three different groups. Now, let us suppose this is my node A and this is my node B. Okay, so currently we can see that node A and node B are not connected. Okay, so currently there's no direct connection between A and B, but we can see that these both belong to same community. Not only they belong to same community, they have a lot of common connections. Okay, so these three are common, if you can see, even this node. So all these neighbors are common to A and B. Okay, so because like these are the nodes belonging to same community. So at some certain point of time, there's very high probability that these both will form a link. Okay, so that's why community detection plays a very prominent role in our further topics that will be link prediction. So we will be studying this topic, that is link prediction, and we will be seeing that how community detection is plays a crucial role while identifying the links between the nodes. So like suppose I have a node A and a node C. Okay, so because these nodes belong to different communities, there's very less probability that in future there will be a connection between these two nodes. Okay, so this is how the link prediction algorithm works, and we will be studying this algorithm in detail in our coming lectures. So secondly, there is one of the application of link prediction, that is recommendation system. Okay, so a recommendation is nothing but application of link prediction. Okay, so in order to design the recommendation systems, it is very important to know that, okay, to what particular community a particular node belong to. Okay, so based on that community, so for example, I belong to student community, and on the other hand, I also belong to professors community. Okay, so based on like my role and my communities, the system could recommend me different things. Okay, so that is how the recommendation system also they require the identification of communities. Now, next comes information diffusion. Suppose I have certain information in my network, and we know that there will be certain groups. And if that information, maybe it reaches to some node here, so that information will first very quickly spread to that particular community. So this community will be the first people who will know this information, and then this information will be broadcasted further. Okay, so in order, whenever we are studying that how the information spreads in the network, again, community detection plays a very crucial role. Then comes market strategies. Okay, so again, there is something called as target marketing. So there are certain products in the market that are maybe formed for kids. Okay, so then there can be certain products in the market that are formed for doctors, maybe. Okay, and so on. Okay, so these products, they are targeting a certain community. So whenever we want to advertise certain product, we have to target these communities. So for that, identification of these communities is very important. Then again, we have epidemics propagation. So epidemic is nothing but studying how the diseases spread in the network. Okay, so generally we have this networks, and then there will be certain nodes that will be sitting in between certain communities. So these will be the nodes with high betweenness centrality. Okay, so whenever we are vaccinating the people, we need to identify this nodes in order to avoid spreading the disease from one community to another. Okay, so for example, we have this information that disease has been spread in this particular community. Now, in order to stop the spreading of this disease to other communities, we have to vaccine these nodes. Okay, so that's another example where again we can see that identification of communities is a very important problem when we are trying to solve the problems related to social network analysis. Now again, like anomaly detection. So how will you identify an anomalous node in the network? Okay, so first you can identify the communities in the network. So after identifying the communities, we can try to understand the properties related to a particular community. Okay, so for example, I have a community in the network, and this community has most of the people who are doing bachelor's. Okay, and then I can see that there is one node or there is one person who is from MTech program. So I can like very easily identify that, okay, this is an anomalous node. So although in the network there can be many people who are who belong to master's program, but like after identification of the communities, we can easily identify the anomalous nodes. Okay, so then evolving communities. Okay, so this is another very important research area in the citation networks. So we have already discussed about the citation network. The citation network is like authors, they are referring to other authors' papers. Okay, so whenever we have this kind of network, so that is called as citation network. So citation network is always a growing network, and the identification of communities in the citation network can help us identify that which particular research area is like people are losing interest in a particular research area. So which is that research area? Okay, so for that area, the communities will be shrinking. Okay, then maybe we can see that, okay, these two are were the interdisciplinaries research areas. Now these are merging. Okay, so you can identify the communities, and then you can do the analysis of these communities over time, and you can, identify these different patterns of how the communities are emerging, how the communities are spreading, how the communities are shrinking in size, what are the reasons behind that. So all those study can be done by identification of the communities. So this year I have done a very interesting a very interesting experiment on evaluation of the communities. So there were no visualizations that could actually help us visualize that how communities grows or shrinks. Okay, so we have formed this dashboard where you can actually visualize the data and see the how the communities, they evolve over the time. Okay, so then there is another application where, like in criminology, it help us to identify the terrorist groups and how these terrorist groups work. Okay, so from this slide, it is very clear that community detection problem is a very important problem. It helps to, solve different types of problems in the social network, like link prediction, then recommendation systems, then, identifying that how the information is spreading or how to stop the spread of a particular disease, how to target certain people in for advertisements and so on. Okay, so for that, now let's try to formulate this problem and let's try to see that what we are trying to do when we are trying to identify the community. Okay, so this is the network. Generally, the networks are huge. They will have a lot of number of nodes and edges. So what we are trying to do is we are trying to identify groups in the network. Okay, so when we try to identify the groups in the network, understanding the network become very easy. Okay, so for community detection, there are certain theoretical reasons and there are certain practical reasons. So first of all, when we are trying to understand the organization of a particular company, maybe, okay. So if you are trying to understand the organization of the node in the company, that like maybe there are a community of managers, and then there are communities of employees, there are the community which is of the staff, and so on. Okay, so whenever you are trying to understand the organization of the nodes, you can identify the communities. Okay, so next is feature identification. So for example, I have this particular community. Okay, so I know the features of all these nodes. Okay, so let us assume that I know the age of all these people. Okay, so now for node A, maybe like there is this missing data and I don't know the value of the age of A. So through the value of these nodes, I can very well predict the age of this node, because we know that there is this phenomena of homophily that is there in the networks, and because of homophily, there is the formation of the structure. And in a structure, there is a tendency that the nodes will have similar properties. Okay, so it helps in a node feature detection. Then also node classification and missing links. So we have already seen that how after identification of the communities, one can identify that whether there is a probability of node A and B forming a connection or not. Okay. So yeah, this is another practical reason for community detection, that is recommendation system. So if you closely observe this particular network, you can see that there are two communities forming here. One is this community and one is this community. This is like based on what they are buying. Okay, so we can see that all these nodes present here, they are buying all these things. Okay, and for this particular node, he has bought the similar items, but this particular node, they have not bought ham. Okay, so now this particular node can be suggested or recommended ham to buy. Okay, so this is how the recommendation systems work. So first you identify the communities, and then you see the patterns of like what all different products the people in this particular community buy, and based on that, the system can recommend the things to a user. So up till now, any doubt, anyone? All right. So with that, I have motivated you enough towards this problem, and we have discussed enough that how identification of communities is going to help us a lot in doing a lot of other tasks in the social networks. Now, this problem is intuitively a difficult problem. Okay. So basically, what we have to do in community detection, suppose I have a adjacency matrix like this. So this is the adjacency matrix for this particular network. Okay, so now I need to form the groups in the adjacency matrix. Okay, so this is called as diagonal block matrix. Okay, so from this matrix, I need to convert it into a diagonal block matrix, and all these blocks, they form the clusters. Okay, so you can see that broadly, I can see these three clusters, the red ones, the purple ones, and the yellow ones. Okay, so these are the three clusters, and then we can see some green, edges in the adjacency matrix. These represent these inter-community connections. So these are the connections from one community to another community. Okay, so right now you might be thinking that maybe this is not that difficult problem, because what we need to do is we only need to shuffle these rows and we need to form these clusters in the network. But imagine you have like millions of nodes. So in that particular case, this problem becomes really difficult, and there is a need to have certain algorithms that can help me identify the groups in the network. Okay, so yeah. So with this, we are convinced that we need to have certain algorithms that can help us identify the communities in the network. Now, let's come to the next topic, that is different type of communities. So now we have studied that, okay, communities are some groups in the network that will have more connections within than the rest of the networks. Okay, but what all are the different types of communities? So the first type of community is the disjoint community. Okay, so in the disjoint community, each node will belong to just one community. Okay, so one node cannot belong to more than one community, and this is called as flat community. Okay, so and like you have seen that like already we have seen that identifying the communities, the flat communities, is a very difficult problem. So now we are moving to next type of problem, that next type of communities. So that is the overlapping communities. So this is a more natural community structure. So in real world life, like I belong to different communities. Okay, so I can be a part of maybe like BITS community. Then like I did my PhD from Triple IT Hyderabad. I have lots of connection in Triple IT Hyderabad, so I might be a part of Triple IT community as well. Okay, so then maybe I'm interested in trekking, so I will be a part of trekking group. So then maybe I am going to gym, I have another community for a gym. So like in real world we are part of many communities, many overlapping communities. Okay, but identification of overlapping communities is a really very difficult problem, but we will be seeing certain algorithms here. Next comes the hierarchical communities. Okay, so what is the example of hierarchical community? So for example, like let me take a university system. Okay, so I might have the students from first year, second year, third year, fourth year. Okay, and these students are further from CSC branch. Okay, so similarly I have student from first year, second year, third year, fourth year from EC branch. Okay, and so on. Okay, so now like these students form further a group of the college they belong to. Okay, then maybe these this different colleges, they can combine to form a group of a city. Okay, and so on. So you can see that intuitively there is a hierarchy in groups or the communities. Okay, so now for these different type of communities, we have different type of algorithm. And this slide, it acts as a taxonomy for different types of algorithms that we have. So we will be studying the community detection algorithms. And in community detection algorithms, we are studying the disjoint communities, overlapping communities, and local communities. So I have missed a slide on local communities. So let me explain you what are local communities. Okay, so generally, like whenever you are seeing a very large network, okay, so suppose I have a huge network of millions of nodes. So one of a very efficient method in order to, identify the communities is to see the node under consideration. So for example, I have this node and I want to recommend this node certain products. Okay, so what I will do is rather than identifying the communities in the entire network, I will see that to which all nodes this particular node is connected to. Okay, then further to which all nodes its neighbors are connected to. Okay, so once I have this data, this forms a local community. So I can study this local community, and based on the study, I can recommend different products to this user. Okay, so these are called the local communities. Local community is when you are considering a node and then you are considering its neighbors and then further the neighbors of neighbors and so on. So when you are trying to study the properties of these neighbors and neighbors of neighbors, that is called as local communities. So we will be seeing all these different algorithms that are node-centric measures, modularity. We will not be seeing this particular method. And then we have dynamic algorithm. Then we have certain algorithms for overlapping communities and local community detection that we will be seeing in our next two lectures. So this is a very important network, and we will be dedicating almost 3 lectures on this topic. Okay. So now let us start that how do we actually identify the communities in the network? So yeah, so before discussing further, I would like to discuss a small um, small historical story about this. Okay, so in the years 1930s, okay, somewhere around 1930s, there was a scientist named as Jacob. So Jacob was a psychologist, okay, and he was trying to understand the properties of students in the class. Okay, so now for that, Jacob formed a handmade graph of the notes. Okay, so he tried to make a handmade diagram of all these people and the connections or the friendship relationships in a particular class. Okay, so while studying this network, Jacob identified that there is a formation of grouping in the network. So these networks are not random. Okay, so he identified this thing that there is the presence of groupings in the social network. Okay, so this was a groundbreaking discovery at that point of time. Okay, so then during 1970s to 1990s. Computers they started gaining popularity, and like there were a lot of algorithms that were done to automate the systems. So during this time, people started thinking about this question, that how do we identify the groups in the network? And by now, the people have started studying little bit bigger networks, like airline, for example, road network, airline network. So those kind of real world network that were little bit bigger in size, people started studying those networks, and they were trying to identify this question, which was still unanswered, that how do you identify these groups in the networks? Okay, so during that time, mathematicians they thought that maybe we can consider graph properties. Okay, so they brought the ideas from the graphs in mathematics, and they tried to identify the groups in the network based on the node properties in the graph. So that is why this is a slightly older methods that were used, and we are going to start our discussion by discussing these methods. Okay, so now like after 1990s, so again, they were again, like they were able to identify the communities based on node properties that we are going to study now. But then like again, they were thinking about this problem more comprehensively. So then came these two researchers, Grivan and Newman. So Newman is a professor at University of Michigan. Okay, so these two professors, they came together and they discovered one very important algorithm that is based on edge betweenness. So we are going to study that algorithm in today's class. And later on, Newman, he also gave another measure that is called as modularity. So modularity is again a very important and very groundbreaking research in network visualization. So the papers of Grivan and Newman, these are the most cited papers in network theory. So yeah, with that history, let us start with our first category of solutions. So that is node-centric, node-centric community detection algorithms. Okay. So node-centric methods, they can be divided into following categories. So first one is complete mutuality. Second one is reachability of the members. And the third one is degree based. So one by one, we are going to see each of these methods. So firstly, we have this method that is based on the clicks. Okay, so what is click? Click is a subgraph where each node is connected to each and every node. Okay, so if you see, this forms a community. Why community? Because here every node is connected to every other node. Similarly, if I see this particular click, that is click number 2, here also every node is connected to every other node. Okay, so initially they thought that, okay, if there is a click in the network, then we can consider that as a community. Okay, but there were certain drawbacks with this method. So firstly, identification of clicks in a large networks is a NP hard problem. Okay, so that's why like it was difficult to identify the group clicks in the network. Then there this they thought that okay, this constraint is very strict. Okay, so we have to relax this constraint. So we cannot go with identifying the clicks in the network. So we have to think about some other method in order to identify the communities in the network. Secondly, like the real world networks are very large, and these are social networks. And generally, there are situations where there are no clicks in the network. Okay, so how will you identify the communities in such a group? So there was a need to identify another method that could identify the communities in the networks. So then they thought of relaxing the condition on the clicks, and they came with another algorithm, that is K clicks. Okay, so yeah, so let's take a short break at this point, and let's come after 10 minutes, and then we will be discussing all the algorithms that fall under this category. Okay, so I have this request regarding the visualization dashboard. So, okay, let me show you one of the dashboard. Actually, the visualization on dynamic networks is not yet published, but then I can show you another dashboard which is already published, and I also have a patent on this particular visualization. So, yeah, I hope my screen is visible to everyone. So yeah, so like I have tried to solve this problem during my PhD that like as you know now we have seen certain visualizations that whenever we try to draw very large networks, it forms a hairball like structure. Okay, and we are unable to see any structure in the networks or any properties of communities as well as the nodes. Okay, so in order to solve this problem, that how do we visualize very large networks? Okay, so this was one of the problem that I was working on. That is, how do we visualize very large networks? Then another part of this problem was that when I talked to stakeholders and the domain experts, I got to know that this is one of the very important question that the domain experts search for. That is, like how do we identify important nodes in a particular network or in a particular community? Okay, so in order to solve these two problems, I came up with this visual solution. So here you can see that there are certain spirals. Okay, so each spiral, it represents a community. Okay, so firstly, you can see that this network is on 4,000 nodes and 88,000 edges. Okay, so this was like before this work was published, this was almost impossible to draw this big networks. Okay, and to take out information or to comprehend such large networks visually. So yeah, so in order to solve this problem, I have the spiral visualization where each spiral, it represents a community. Okay, now if you see this visualization, you can easily see, okay, which is the bigger community or which is the smaller community and so on in the network. Okay, so this is one of the property, that is size of the communities. So seeing these spirals, you can comprehend the size of the communities in the network. Then like there is the edge density within the communities. So I have encoded that using the colors. Okay, so red color, it represents high density in the communities, and blue color represents the low density. Okay, so now after density, you can see that there are certain gray edges in this spiral visualization. So the thickness of the edges shows that like how many connections are there between two communities. So for example, I can see there's a very thick edge here. Okay, so it shows that this community and this community has a lot of connections in common. Okay, also from this visualization, I can see that which particular community is connected to which all other communities. Okay, so then like we have nodes in the network. So what I have done is I have ordered the nodes based on centrality, and then like I have placed the nodes starting from the center of the spiral, such that the centermost node is the most important node, followed by less important nodes. So if you hover on a particular node, you can see that here a node has 110-degree. Okay, but if I move towards periphery, the degree of a particular node is 8. Okay, and maybe if I move even further towards the periphery, the degree of the node is 1. So then there were certain other features. I can rank the nodes on any of the degree. Okay. So now seeing this visualization, one can easily identify the important nodes in a particular community. And like if you hover on a particular node, you can also see to which other nodes this particular node is connected to. Okay. So you can see node connection, node centrality. Then for the communities, you can see community size. Then you can see the edge density in the communities. You can see edge connections of the communities. You can also see the distribution of degrees or the centralities in community. So let me show you. So there is this color coding. So currently the nodes are ordered based on degree. So if I change the color coding, Okay, so now the color coding is based on degree centrality. So all the blue nodes are the nodes with lesser degree. Then yellowish nodes are the nodes with the greater degree. Then we have reddish color for the nodes that have high degree, and we have the black nodes. So these are the black nodes are the nodes that have very, very high degree. Okay, so we have studied in power law distribution that in social networks there will be few nodes that will have very, very high degree. Okay, so all the nodes that are colored black, that are the nodes that have very, very high degree. So for example, you can see this particular community. So seeing this visualization, one can easily comprehend, okay, this is the community and this is the community that has a lot of node with very, very high degree. So that is why maybe we can say that this community, although it is smaller in size, but it is a very important community. Okay, so these are all the different things that you can comprehend through this visualization, which was earlier not that easy to comprehend. So this was one of the work, and then I have also developed another solution. So here, but in this solution, there were certain problems. So one of the problem was that node near the center are very tightly packed, whereas if like the community size increases, the separation between the nodes increases. So one of the problem was like I further wanted to scale the system. So this system was currently scalable up till 10,000 nodes. So what if I want to visualize now 50,000 nodes? So how will I do that? So maybe in that I'll have very big spirals. So if I have big spiral, as the size of the spiral increases, the distance between the nodes also increases and the spirals may overlap. Okay, so then we have another solution that is called as linear solution, in which we placed the nodes in linear fashion in order to avoid this particular problem in this system. So these are the two systems that I developed, and on both of these, like on this particular system, there's already the patent that has been granted. And then there was another solution that I told, linear visualization. So on linear visualization, we have filed the patent, but it has not yet been granted. So, and then there was this work that I was talking about like visualizing the community growths in the network. So that work is like still submitted to a very good conference, and we are still waiting for the results for that work. So yeah, so we have slightly deviated from the topic. So now coming back to the topics that we were discussing. Okay. Okay. So before going on break, we were discussing that how do we use the node-centric measures in order to identify the communities. Okay. And the first method we saw was identification of the clicks in the network. Okay. But then we saw that this is a NP-hard problem and one cannot use identification of clicks to identify communities in the large network. And also like real world social networks, they are generally not like there's generally not the presence of clicks, so this method cannot be used. So then there is the second method that we were discussing, and this method is called as k-clicks. Okay, so what this method says, so now there will be like a few definitions on the K clicks and K clubs and some very similar terminology. So there will be few definition. Please try to understand the difference between these definitions very clearly. Okay, so you need to focus on the next few slides. Okay, so now first of all, what is the definition of K clicks? Firstly, K click says that there is a maximal subset of the nodes. Okay, so there will be a maximal subset of nodes. So the term maximal is very important, and I hope you understand this term called as maximal. So anybody can explain me what is maximal? What do we mean by maximal? So you might have heard this word in set theory, maximal subset. So what do we mean by maximal? Anybody can tell me? Okay. So let me take an example to explain this. For example, I have a subset, maybe A, B, C, D, E, F. Okay. And then maybe I have a function F. Okay. And F adds A and B. Okay, so when f adds a and b, let us suppose the value of a plus b is 0.7. Okay, so now let us suppose I take another function a, b, and c. Okay, again, when I try to add a, b, c, the summation comes to 0.7. Okay, so now in this case, you can see that we have added one extra element, but still the summation remains the same. So this particular function a and b, having a and b, is not a maximal subset. Okay, so a maximal subset is a, b, c. Okay, so then let us suppose we have another function, maybe like a, b, c, d. Okay, so now when you try to identify the summation of these values, it reduces from zero point 0.7. Okay, so now this ABCD is not a maximal subset. We are not going to consider the ABCD. Okay, so here the function is trying to identify the maximum sum. Okay, so now again, let us suppose we have another subset of maybe D, C, E. So DCE is also zero point 0.7. So here you can see that both ABC and DCE are the maximal subsets. So let us suppose maybe I have another subset that is A, B, F, and E. Let us suppose, and its sum is also zero point 0.7. So here this is also a maximal subset. Okay, but now let us try to understand what is the difference between maximal and maximum. So if we consider the size of this subset, so this has the maximum size. Okay, why? Because there were four entities here, but here there were three entities. So I hope you understand the definition of maximal with this example. Is it clear to everyone? What is maximal? Okay, have I unmuted you all today? Okay. So I forgot to unmute you today. All right. So firstly, the subset that we are considering for k clicks has to be maximal. Okay. And then for any two nodes belonging to this subset, the shortest distance between them is less than equal to k. Okay, so if we are considering k-click, we have to consider the maximal subset of nodes such that the shortest distance between any two nodes in this particular subgraph is less than or equal to k. Okay, so for example, let us consider the highlighted nodes. Okay, if you consider these highlighted nodes and you try to see the distance between any two nodes in the network. So if you try to see the distance between any two nodes in the network, you can see that the distance between any two nodes in the network is maximum 2. Okay, so for example, 3 to 2 is 1, 3 to 1 is 2, 3 to 6 is again 2. Okay, so 3 to 2 and 2 to 6. Now, if I want to go from 3 to 5, 3 to 5 is again 2. Okay, so now there is one very important thing to see in this particular example. So there is this node 4. although 4 is contributing to shortest distances that we are considering in the definition of click, but 4 is not included in this subset. So the definition of k click, it does not say that the induced subgraph should itself has the shortest paths. Okay, so I can have a shortest path passing through a node that is not part of this k click. Okay, so now there was again, this is one of the issue in this particular technique. So there can be a node that is present in k-click. A node not present in k-click can contribute to the formation of the shortest distance. So then they thought that maybe like this is not a very good definition. So maybe like I should make this I should, implement this condition that the induced network, the induced subgraph itself should have the shortest paths. Okay, so I should not consider any node that is outside the node for outside this K clan for the shortest paths. Okay, so is the difference between these two clear to you? So I will repeat this again. So when we consider the shortest paths in this particular example, we saw that there was a path that was passing through a node that was not part of 2-click. Okay, so this is 2-click. And there was a node that was not part of this 2-click, but it was contributing to the shortest path. Because from 3 to 5, if I want to go, the shortest path is of length 2 is through 4. Okay, so then we have another measure that is called as k-clan. So k-clan says that like it is a stricter version of k-click. Okay, so how stricter version of k-click? Only the nodes present in the set under inspection are used to create the subgraph in which the distance between any two nodes should be less than or equal to k. Okay, so we have to use only the induced graph in order to find the shortest paths. Okay, so we cannot use any node that is not part of this induced graph. So here, let us assume this example. 2, 3. So if we are considering this example, can anyone tell me that what is the value of k if we are calculating k clan here in this particular graph? Okay, can anyone tell me what is the value of k in this case? So k is the shortest distance. So the shortest distance to any node, any pair of nodes should be less than the value of the k, less than or equal to. So for that, we need to identify the distance between pair of nodes. Okay, so let me check. The distance between 2 to 3 is 1. Distance between 2 to 4 is 2. Then 2 to 5 is again 2. I can follow this path. So the distance will be 2. Distance from 2 to 6 is 1. Okay, so I can see that each node in this network can be reached with a maximum distance of 2. So this forms a K clan. Okay, so now let me ask you another example. Suppose I have these nodes. Can I say these are 2 clan? Can I say these are 2 clan? Class, please try to answer the question.
Yes, ma'am. It is 2 clan.
Okay. The answer is incorrect. Why? Because in this particular set of nodes, the maximality condition is not met. So initially I told that the subset of nodes should be maximal. Okay. So here, this is like if we add node number 6 here, or if we add node number 5 to these particular group, still they are K clan. Okay, still they are two clan. So if I add 6 and 5 to this particular subgraph, then still it will be a two clan. So that's why this is not the maximal subset. So that is why this is not a K clan. Okay. On the other hand, if you see this particular example, you can see that this particular subgraph that we are considering, is it K clan or not? Is it two clan or not? So I'm considering this particular graph 1, 2, 3, 5, and 6. Is it two clan? Please check and tell me. Please check and tell me that is it two clan. For that, you need to identify the distance between the nodes. Anyone? Class, please try to answer yes or no. It's okay if it is wrong.
Can you repeat the question, please?
Okay, so if I'm considering this graph 1, 2, 3, and 4, the highlighted one. So can I say this particular graph is two clan?
No, ma'am, we can still add 5 and 6 and it will be two clans, so it might not be the.
Okay, so the answer for this is whenever we are checking clan, we check the induced subgraph. So what is the induced subgraph for this? The induced subgraph is 2, 6, 3, 5, and 1. Okay, so now like all the shortest paths I have to calculate only from this subgraph. Okay, so I cannot consider this fourth node as it was considered in K-click. Okay, so now I will try to check the distance between each and every node. So 3 to 6, if I want to reach the distance will be 2. 3 to 5, if I want to reach the distance will be 3. Okay, so this particular graph is 3 clan. Okay, so it is not 2 clan, it is 3 clan. So 3 clan also again I have to check the maximality condition as well. So currently I have only checked the distance. So there are these two conditions that needs to be checked. One is the maximality condition and the other is like the maximum distance. The maximum distance should be less than or equal to k. So definitely it is not 2 clan. So that is the definite answer. But 3 clan, I'm not sure. I need to still need to check the maximality condition. Still need to add 4 and 7 and check that whether like is it a 3 clan or not. So I think if we yeah, so that you can check as part of the homework.
Excuse me,
So
ma'am.
yes.
But if we are, it's a induced graph, then the moment we had considered 3 and 4, oh sorry, 3 and 5. So if it is like vertex induced graph, so 4 will be considered automatically as a part of bigger graph. No,
Yes, yes. So if I'm considering 4, then the induced graph will be this one.
and then it will become two clan.
Yeah, then it will become 2 clan. Right.
Okay.
So now let us also try and add 7 as well. So if we have 7, then it will be 1 from 3 to 1, 2, 2, I think it should be 2 clan only. Am I right or wrong?
But the distance from 2 will become 3, man. This
2, 2,
7.
1, 2, 3. Yes, it's 3 clan. Right. So if we add 7, then it is 3 clan. So I hope the difference between K click and K clan is clear to you. Any doubts, anyone? Okay, so again, now there was one drawback with this particular technique, that is K-clan. Okay, so one is checking the maximal condition was difficult. Okay, so in this smaller graph only we can see that checking the maximality is a difficult problem. Okay, so when you have very large networks, then checking this maximality condition will become difficult. And on the other hand, it was very difficult to identify that what should be the value of K. Okay, so because this technique has these two problems, then they came up with another measure that is called as K club. Okay, so in K club, K club is very similar to K clan minus the maximality condition. Okay, so if I do not apply the maximality condition, all the subsets that I am getting, that is called as K club. Okay, so now if I have this particular group of nodes, this will be called as two clubs. Okay, if I have this subset, that will also be called as two clubs. If I add these, if I check these three nodes, that will also be two club. Okay, and based on these two club definition, they tried to identify the communities. Okay, so now in this particular technique, there were two challenges. One is that these algorithms are still computationally expensive when we have large value of k. And also, again, deciding the value of k was difficult. So now there was another measure that they identified, and that is called as k-plex. Just give me a moment, class. Okay, so then we have the definition of k-plex. What is the definition of k-plex? The subset of vertices is in the graph is k-plex if every vertex in the induced subgraph. So here again we are considering induced subgraph. Okay, so if every pair of vertex in induced graph has degree at least s minus k, where s is the size of that induced subgraph. Okay, so now for example, let me consider 3, 4, 5 and 6. Okay, so let's try to understand that what will be the k plus what will be the value of k in this particular induced graph. Okay, so I have this induced subgraph 2, sorry, 6, 3, 4 and 5. Okay, so we have this subgraph. So what is the size of this graph? So can anyone tell me what is the size of this graph? Size
4.
means number of nodes. Yes, correct. So the size of this node is, this particular graph is 4. Okay, so now let us try to identify the degree. Okay, so in this particular graph, each node has degree 3. Okay, so we will try to identify, in order to identify the k value in k-plex, we will try to identify what is the minimum value of k. Okay, so here we have k is equal to 3. So we will subtract 4 minus 3, that will be equal to 1. So this is one plex subgraph. Okay. So what was the definition? The induced subgraph has degree at least k. Then we call it as a k-plex. Okay. So now let us take another example. So suppose I'm taking this subgraph. So let us suppose we are taking this subgraph. Okay, this is okay. So now in this subgraph, what will be the k value in k-plex? So firstly, we'll
Then
identify what is the sizes.
5,
Yeah, yeah, anybody is trying to answer the question. What is the answer?
2, ma'am.
Okay,
Five,
It will be
five.
2 plex.
yeah.
Two
So
plex.
we'll try to check the value here. So the size was 5 and the minimum degree in this graph is, I think, 3.
3.
Yeah. So 5 minus 3 is 2. So this is a two-plex graph. So the researchers, they used these different values in order to identify the communities in the network. Okay, so there is another slide
Ma'am,
missing.
may I ask a question?
Yes.
The first example which you had taken 4 nodes, 3, 4, 5, and 6, and that became one plex when
Hmm.
we subtracted 4 minus 3. But
Hmm.
same graph, uh, it is 2 plex also, because each node has got, in fact, in 3 connections. So it can become 3 plex also. The same 3, 4, 5, 6 can be 1 plex, 2 plex, and 3 plex, because those minimum number of connection each node is having. Although formula is telling 4 minus 3, 1 only, but if we
Mhm.
go by the definition, then
Hmm.
each node has got 2 and 3 connections. So is it possible, or it is just the
Okay, let me check. So the degree should be at least k. So you're saying that if I insert the value 2 here, so if I insert in the previous formula, we had the size as 4 and
yes,
we
ma'am.
insert the value of k as 2.
3.
Okay,
We
so
can
if
insert 2 also.
so if I only then it will be two-plex, right?
2 blocks, yes, ma'am.
So in that case, like the minimum degree should be 2. 4 minus 2 is 2.
Yes,
But
ma'am.
in this
2.
particular graph, the minimum degree is 3. So that is why we cannot say that it is a duplex.
Okay.
Oh, sorry, I haven't shared the screen. So yeah, so I hope this calculation is clear to you. So there were 4
Yes,
nodes
ma'am.
and we have inserted the value 2. So we got 2. So 2 should be the minimum degree in the induced subgraph. But we can see that the minimum degree is 3. So that is why it is not duplex, it is one plex.
Okay.
So there is another definition that is missing. I'll show you in the slides. Okay, so then this is the last node-centric measure that was used for community detection. Okay, so what they used is they used the definition of K-core. So what is K-core? First, they try to remove all the nodes with the degree 1. Okay, so they will keep on removing the nodes of degree 1. So once they have removed, so suppose they have removed all the nodes with the degree 1. Okay, so again, they will see whether there is any node with degree 1. So they can see that, okay, this is when we remove these two nodes. Okay, so when you remove these two nodes, again, degree of this node will be 1. So they will again remove this node. Okay, so all the nodes that are removed of degree 1. Okay, so when I have no node with degree 1, so that is called as one core nodes. So all those are all those are considered as one first community. Then like they try to remove all the nodes with degree 2. So if we remove all these blue nodes, we will have all the nodes with degree 2. There will be no node with degree 1. Okay, so all these nodes are two core nodes and they form second community. So similarly, they will keep on removing all the 2 degree nodes until I have no nodes with degree 2. Okay, so then like if you see, if like we remove all these connections, okay, if I remove this particular connection, this connection, this connection, this connection, all these external connections are removed. So now if I see, I am left with the nodes that have degree greater than 2. Okay, so all these nodes, they form a third community, that is third core. Okay, so this was another method that was used to identify the communities. So you can see that the scientists, they used different methods. Okay, so they were using a lot of concepts from maths to identify the communities in the network, and the definition was communities was not fixed. Okay, so they somehow wanted to quantify the structures in the graph, and they were using a lot of concepts from the graph theory, but like they were actually not able to come up with a satisfying solution that can be applied to large social networks. So then this was another method that was very convincing, that is based on cut. Okay, so now currently we have covered, I think, all the methods that are there for that are node based. Okay, so here we have covered the clicks, k clan, k club, kplex, and k course. So these were all the methods that were based on node measures. Okay, and we have covered all these methods. So next they thought that, okay, why not consider the edges? Okay, so once they have exhausted all the techniques, and there were some more techniques that maybe I have not covered in this lecture. So yeah, I basically, like, I have given you the idea that there were different techniques that were node-based techniques. So once they covered these techniques, the scientists started thinking that can we use the edges to identify the communities? Okay, so then came this concept of cut. Okay, so this was a concept that was already there in the graph theory. So they used this cut concepts in order to identify the communities. Okay, so what is cut? Cut, a partition of the vertices of a graph into two disjoint sets. So what is cut? Cut is we delete few edges and then we get disjoint subgraphs. So now what is minimum cut? Okay, find a graph partition such that the number of edges between two set is minimized. Okay, so the number of edges that we are cutting, that should be minimized. So this was one of the problem, that is minimum cut. Okay, so now when like they were studying the concepts of cut, okay, so they discovered that, okay, like maybe if I cut this particular edge, here I only have to cut one edge and I get two disjoint subsets. Okay, so yeah, so if we cut this particular edge, okay, my pen is not working. Okay, so if I cut this particular edge, okay, so if we cut this edge, we will have two subgroups. One is 9 and the rest subgroup is this entire network. Okay, and like there can be another cut where we are deleting these two edges and then we are getting two groups. Okay, so you can see that there was a problem with minimum cut. So whenever you are trying to, use minimum cut to identify the communities, so you can get imbalance in the communities. So there's one community with just one node and then there is another community with so many nodes. Okay, so you want to have balanced communities. So how can you have the balanced communities? communities. For that, like they came up with these two measures. So one is a ratio cut and the other is normalized cut. Okay, so here K is the number of communities that are forming after deleting the edges. Okay, and like cut value, it represents the number of edges that you have to cut, and in the denominator, I have the size of community. Okay, so you will be considering each community. You will be considering in the numerator, you will be considering the number of edges that have been deleted, and in the denominator you will be considering the size of the community. Okay, and you will be forming a summation on all the components. So with that you will obtain the ratio cut, and we need to minimize this ratio cut. Okay, so you need to minimize the value of this ratio cut. Then we have another mathematical notation, that is normalized cut. So in normalized cut, like rather than using the size of the subgraph, okay, the size of the community, we use the summation of all the degrees in the subgraph. Okay, so now let us try to calculate these two values. Just a second. So I'll show you the calculation of these two values. Okay. Okay. So yeah, so firstly, we are considering this partition. Okay, so this is one community and this is another community that you identify by using cut. Okay, so now we will try to identify what is the ratio cut. Okay, so ratio cut will be 1 by k. So you have this formula 1 by k where k value will be 2. Okay, why k value will be 2? Because we have these two communities. Okay, so this will be 1 by 2. And then like this is how many edges you have to cut. So here you have to, in this particular partition, you have to cut just one edge, right? So you have cut just one edge, and then we are going to see the size of each community. So we are going to do summation on all the components that are formed after the cut. So we have two components. Now, how many edges we have to cut for this? One edge. And if we consider this, what is the size of this community? The size of this community is 1. Okay, so now we will do a summation. So now we will consider another community that is formed. How many edges we have to cut? That will be in the numerator, that is 1. And now how many nodes are there in this community? So there are 8 nodes. Okay, so this will be the ratio cut for this particular partition. Okay, so this value is 0.56. So I hope the calculation is clear to everyone. Okay, so now for this partition, let us call this partition as pi1. Okay, so for this partition, we are also calculating normalized cut. Okay, so in normalized cut, again, we have the value of k. So since there are two partitions, so this will be 1 by 2. Okay, and then for each community, we are going to see how many edges we have to cut. We have to cut just one edge. Then we are going to see in this particular community what is the summation of all the degrees. So summation of degree is 1, right? So summation of degree is 1. So we have this value. Then we will add for another community, that is the second communities. Again, we are going to see how many edges you have to cut. You have to cut just one edge. And in the denominator, we will put the summation of all the degrees. Okay, so now you can check what is the summation of all the degrees in this particular community. This is 1, 2. 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 2 is 10. 12. 12 and 12 plus 4 is 16. 16 plus 4 is 20. 20 plus 4 is 24. Then we have these 3 degree. 23 plus 4 is 27. So that is why we have 27 in the denominator. Okay, so this is the normalized cut and this is the ratio cut for this particular partition. So similarly, you can calculate the partition, the ratio cut and the normalization cut for the another partition. So what is another partition? So up till now, is the calculation clear? Is these two matrices, that is ratio cut and normalized cut, how we are calculating it, is it clear to everyone?
Yes.
Okay, sure. So then we have another partition, that is this partition. Okay, so if we consider this partition and we are calculating ratio cut, okay, so again we can see that there are two communities that are formed. How many edges you have to cut? You have to cut two edges each. So in the first, for the first community, how many nodes are there? 1, 2, 3, 4, 5. So one community has 5 nodes and another community has 4 nodes. Okay, so we will have 2 by 5 and 2 by 4 here. So this will be the ratio cut for this particular partition. Also, we are going to calculate the normalized cut. So in normalized cut, again, we have this value. So here we are again going to calculate the summation of all the degrees in first community and the summation of all the degrees in second community. And those values, we are going to put it in the denominator. And this is the value. So is the calculation clear to everyone? Any doubt in the calculation of ratio cut and normalization cut? Okay, so if that is clear, then after suppose I have these two partitions, that is pi 1 and pi 2, and I want to calculate that which particular partition is better, okay, and more balanced. So in order to identify that, we use ratio cut and normalized cut, okay, and we need to see that which one is the minimum value. So if we compare these two values, we can see that the partition 2 is better. Also, if we check the normalized cut value, so again, we can see that the value of partition 2 is lesser than that of partition 1. Okay, so that's why these two matrices, they suggest that the second partition is much more balanced than the first one. So yeah, so this was one of the technique. So then, as I have explained you about Grivan and Newman. So these were two researchers who were extensively working on this problem as part of their PhD thesis. Okay, so now while working on this problem, they tried to solve this problem in as the detectives. Okay, so first they try to see that, okay, what is community, what are the structures in this community. So basically they saw that, okay, the communities are something that have more interconnections with it. Okay, and then they saw that, okay, there are certain bridges that connect these two communities. Okay, so you can see that maybe this is a community and maybe like this is another community. And they saw that there will be very few connections that these that connect these two communities as compared to the number of connections that are there within the communities. Okay, so now how do you quantify the bridges? Okay, so then like they came up with this idea of betweenness centrality. So when we calculated the betweenness centrality, you saw that these two were the groups, and there was one node. Okay, and this node has high betweenness centrality if there are a lot of shortest paths that are passing through this particular node. Okay, so how do you quantify the betweenness? Betweenness is the number of shortest path that is between any pair of nodes that are passing through a particular node. Okay, so that is how we quantify the betweenness of a node. So they extended this definition to the edges. Okay, so now in this particular case, we are going to calculate the number of time a particular edge appear in the shortest distance between any two pair of nodes. Okay, so by quantifying the value, they identify betweenness of each edge. Okay, so like if I give you a high level algorithm of edge betweenness, what it is, first they identify edge betweenness of each edge. Okay, so they quantify that like which edges appearing on in between the shortest paths. So they calculated the edge betweenness for each edge. Then like they tried to remove those edges that have high betweenness centrality. Okay, so one by one they removed the edges, and then iteratively they again calculate edge betweenness for entire network. So whichever edge has the highest edge betweenness, they will remove that edge. Then again iteratively they will try to identify the edge that has highest betweenness. So the one with the highest betweenness will get removed. Okay, so now in this example, and like with this, you can form the partitions. Okay, so I will be showing you another diagram which will be explaining this edge betweenness algorithm more clearly. So before that, let us see that how the edge betweenness is calculated. Suppose we need to calculate the edge betweenness of edge 1. Okay, so now in this case, we will be considering all the shortest path. Okay, so for example, the shortest path from 2 to 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you have to consider the shortest path from 2 to all the other nodes. Okay, so now when you are calculating that, firstly, we are considering 1 to 2. So from 1 to 2, there is only one shortest path, and like that is passing through this particular edge. Okay, so this contributes to the edge betweenness. Now we will calculate between 1 and 3. Okay, so when we are calculating from the path from from 2 to 3. So from 2 to 3, we need not go through 1. Okay, so in that particular case, this particular edge do not contribute to edge betweenness. Now let us consider from 2 to 4. So if I want to go from 2 to 4, so now let us try to first find that how many shortest paths are there from 2 to 4. So there is one path from here to, there's one path from here to here, and then there's one path, shortest path from here to here. So you can see that there are two shortest paths. So from these two shortest paths, there's one path that is passing through this edge. So this will be 1 by 2. Okay, so now let us consider from 2 to 5. So I'm considering from 2 to 5. So can anyone tell that how many shortest paths are there from 2 to 5?
M2.
Yes. So one is this path and the other is this path. Okay, so there are two paths, and out of which one is contributing to the shortest path. One of the path is passing through this particular edge. Okay, so then again we are going to calculate for 6, 7, 8, and 9. For all these nodes, the value will be 1 by 2, 1 by 2, and so on. Okay, so this will be, this was for 1 to 2, 1 to 3, there was nothing, 1 to 4, 1 to 5, 1 to 6, 1 to 7, 1 to 8, 1 to 9. Yes. So this will be 6 by 2 plus 1. Okay, so this will be equal to 4.
4.
Okay, so this will be the edge betweenness. So in this way, you will calculate the edge betweenness of all the edges. Okay, and once you have identified the edge betweenness of all the edges, you need to delete the edges with the maximum edge betweenness. Okay, and if you keep on iteratively calculating these edge betweenness and removing the edge with the maximum edge betweenness, you get the communities. And you have to see where, like, for example, you need 3 communities. When you get 3 communities, you will stop. Okay, so depending on your need, you can stop. So for example, this is also shown in this particular example. So we have converted this particular graph to the adjacency matrix, and from the we have also calculated edge betweenness. Okay, so this is the edge betweenness for edge from 1 to 2. And this is the edge betweenness. I hope this diagram is clear to everyone. Okay, so we have calculated these edge betweenness. Okay, so from 1 to 4, the edge betweenness of edge 1 to 4 is 9. Okay, and so on. So now you will try to identify what is the maximum edge betweenness. The maximum edge betweenness is between edge 4 to 5 and 4 to 6. So let us see. So these two edges are currently having the maximum edge betweenness. So what you will do, you will remove this edge and this edge. Okay, so you will remove these two edges and you have these two components. Okay, so now, for example, again, you want to you want to have more than like you want to have 3 clusters. So what you will do, you will again so now you have this subgraph and this subgraph. Okay, and again you will calculate the edge betweenness for this entire system. So when you calculate the edge betweenness of this particular edge is maximum. Okay, so after this, you get this partition. You have this community, then you have this community, and then you have this particular community. So this is how edge betweenness works. Okay, so now there is another measure that is called as modularity measure. So modularity, ab dekho, this Newman and Grivan, they came up with this algorithm which identify some communities. Okay, so ab unke paas communities aa gayi. So now the next problem they started working on was very natural. They started to identify or to quantify that. Suppose I have a community. So how can I say that this is a good community or this is a better community than the other community? So they try to mathematically quantify the goodness of a particular community or a community detection algorithm. So for that, we have this measure called as modularity. So we will be covering the algorithm on modularity in the next lecture now. And like this is a very popularly used algorithm, the modularity algorithm. Okay, so the modularity algorithm is very well and very popularly used in like a lot of research papers. So whenever we try to identify the communities of very large graph, we use this matrix called as modularity. So we will be discussing this measure in our next lecture. So yeah, so with that, we will end our today's lecture. I hope you enjoyed the lecture and you understood all the concepts that I have discussed today. And so with that, any questions anyone want to ask?
So, ma'am, can we get the communities by node betweenness as well?
Node
Just like,
betweenness. Yeah, there must be some algorithm that would have used node betweenness as well to identify the communities. But yeah, the algorithm that we have covered in the class, that is this Newman-Griven algorithm. So that was a very popular algorithm. So, but definitely there will be some research papers that uses node betweenness to calculate the communities.
Yeah, I think so.
So, any other thing anyone want to ask? How was your mid-sem paper? Was it easy, difficult? How it was?
It was okay,
It
man.
was okay, but I did not expect the derivation of eigen centrality.
Mm-hmm. Okay, okay, sure. So yeah, because like there were only 6 lectures that were covered before midsem. So we missed on 2 lectures. So the portion was very less. So that's why, and there was one entire dedicated lecture for that particular derivation. And like even in the class, I told that you need to focus on this topic. This can be asked. So yeah. So that was the reason like I had to put the derivation in the paper. Anything else? Any other feedback or any other comments?
Else, it was good, man. Yeah.
Okay, okay, sure. So, yeah, with that, we will end this lecture. Thank you for being a lovely audience. Enjoy your Saturday. Bye bye.
I have one
Okay, thank you.
question before you.
Yes,
I
yes,
have
yes.
sent an email regarding the quiz one. I haven't got my grade yet.
Okay, so quiz one, that is not like we are not the one who are uploading the marks and calculating the marks. It is calculated by the system. So how it is like in the other subjects, are you getting to see the grades in the quiz? So how it is? Let
Yes,
me know.
yes,
Okay, okay.
yes,
If
Miss,
that
we can see the grades and sometimes even the answer. Yeah.
Okay, okay. So if that is the case, I'll talk to Sai sir. I'll talk to him and I'll ask him that why, like for this particular case, students are not seeing this the grades.
Okay. I've
And
sent
I'll
you an email related
yeah,
to
yeah,
that with a
I got
screenshot.
that.
Yeah.
Yes, yes. Okay,
Thank you.
sure, sure. Thank you, everyone.